Hey everyone, thank you for joining in. I know it's been a long day and you've been to a lot of talks, so I'll try to keep this pretty high level, short, and hopefully something which you can take away from. So today I'll be talking about some of our work where we applied reinforcement learning on controlling large commercial cooling systems in buildings such as this, right? Before I go too deep into that, I can start by motivating the problem, as in why is this something we've been doing. For those of you who have been in Vegas or stepped outside the hotel, you can appreciate it's quite hot. It's not the most comfortable to be in. But the truth of the matter is, it's actually been getting warmer over a much lower frequency over multiple years, decades, and even centuries. Oops, that should have kept playing. So this is alarming, and soon we are going to be reaching an inflection point where this could have wide repercussions on our ecosystem and the planet, which we call our home. So we focus on one specific aspect or one specific one specific reason on why we have this sort of issue today. Industrial systems are one of the largest causes of greenhouse gases. They emit approximately 34% of total emissions, but this is also increasing 1% annually. So there are two issues here, right? It's a vast majority of the overall contributions towards greenhouse gas emissions, but it's also increasing in absolute numbers year on year. So finding a way to make this more efficient and at least curb the rise in this is something which is of utmost importance, especially keeping our planet in mind. So us being DeepMind, we tackled this the machine learning way, right? We used deep reinforcement learning. This project started off with Google data centers where they applied a reinforcement learning agent and they achieved 40% energy savings. And more recently, looking at the news clippings, which you can see here, we were able to apply this to external commercial facilities similar to the scope of buildings such as this, and were able to optimize the energy bills by 10%. Today, I'm going to talk a bit about how we did it, or at least one of the approaches that we took internally so as to kind of make this happen and help us better understand the field overall. So when we talk about reducing the energy bills in cooling systems, what you need to understand is the way it's typically done right now is there are human operators, software engineers like me, who write heuristic-based code. And based on that, they said, oh, if it's too hot, increase the air conditioner up a few notches, so we reduce the temperature, right? This can get complex real quick. The major sources of heat is not just humans, but there are also daily patterns, seasonal patterns, even random patterns. Let's say there's a storm coming up. And keeping track of all of this is quite hard. Now, if you think this is hard for a human, for something like a reinforcement learning agent, this just makes it 100x as hard. The reason for that is these reinforcement learning-based approaches, they are increasingly data hungry in the sense that they're very sample inefficient, and it requires a lot of interactions with the environment, in this case, a real-world cooling center, for them to be able to work well. And secondly, another factor with this is that reinforcement learning agents, they want to explore. So if you think of it, if you want to be able to control a cooling system efficiently, you need to know the limits of what you can do, right? I wouldn't be very comfortable with telling a reinforcement learning, here's an entire industrial building, turn on and off whatever you want, and let's just see what happens, right? Doing that in the real world can be catastrophic. So this kind of motivates the need for a sort of playground or a test bed for these sort of agents where they can kind of explore safely, learn over these simulated data centers, and then once we're confident they work well, we can then move on to the real world. And so again, being DeepMind, what we created was the industrial task suite. We published this and a couple of other papers at NeurIPS last year. But basically, for those of you familiar with reinforcement learning, it's a simple extension of the paradigm where we extended a reinforcement learning library specifically tailored for industrial buildings. You don't have to go too deep into details, but basically what I'll be talking about right now is the environment, which is an industrial building such as this. But we also added a lot of bells and whistles, such as random doomsday simulators, noise generators, random initial conditions, such that we could have a lot of flexibility in this sort of parameterized simulation environment which we created. So let's talk a bit about this environment, what you see. Let me just get my mouse pointer on. Yeah, so you see this environment. This is the crux of what we're simulating. Let's talk a bit about what that is on a super high level, 45-second kind of debrief. All of us, we are in the room right now. We are all carbon-based life forms. We are emitting heat. The hot air rises up. There's something called an air handling unit, which isn't super visible here, but believe me, it exists. That absorbs the hot air. It cools it down, so we have cold air, the air conditioning. So it's a bit too chilly for my liking. But basically, we have a water-based system that cools that. And you see this red tube over here. That's basically the water-based system that goes to another obscure part of a building called a chiller, which most of us will never see. And then that is also cooled by something called a cooling tower. So if any of you have been to like the rooftop of buildings, you see those clunky, loud machines. That's a cooling tower, which uses this latent heat evaporation to cool it. But what you need to just take away from this is that this is a fluid-based cooling system. There are a lot of control mechanisms that control the parameters of the fluid, the temperature, the flow rate, the pressure, and that's what this sort of control mechanism through reinforcement learning is what we're trying to optimize for. So, and this is what we actually simulated. It's quite complex. I had a few slides on how we did it, but that's beyond the scope of it. Let's just skip to the results of like how we managed to simulate a large-scale system. You see these colorful plots over here. These basically just represent different physical variables, such as the temperature, pressure, and I think flow rate of water through the system I showed you before. And you see these two plots on the right. Those are basically just the reward for those of you familiar with reinforcement learning, which is basically how well it's doing at a certain task, of a random dummy agent we plugged in to test it end to end. So we spent 6 months developing this, and yeah, we finally got this working end to end, which was great. So now we could do the fun stuff. Now we could actually plug in a reinforcement learning agent into the suite we have created and see how well it does. And just to keep in track of the end goal, we want to make sure that this could be transferable to the real world, even though we're working on a simulation right now. So we now have this super powerful simulator, and we have a bunch of existing reinforcement learning agent baselines. How do we kind of like make this magic work, right? So we designed a concept of something called tasks, and those are basically different simulated scenarios which you want an agent to learn in. Obviously, we can start off with like the complete NP hard one and just try to solve that. So we used the approach which might seem reasonable. We started with like super simple things to train an agent on, which is like saying that, oh, there's an air conditioner on. If you turn it off, will you save power or will you use more power? That's obvious to us, but believe me, it takes a lot of time for an agent to figure that out. So we started with that over here. You see this task complexity easy. That's what we started with. And then gradually we started increasing the complexity to something, well, we just have a medium here. I don't have a hard, but we have something like, oh, reduce the amount of energy used by 3 chillers. You can think of chillers as air conditioners. 3 chillers while maintaining a temperature in a certain zone within the range. But also I'll randomly initialize the starting condition, so that makes it harder. So that just gives you a flavor of the kind of stuff you're trying to do, which really mimics what we see a lot in the real world. And we actually got reasonable results. These are just a few plots of us on the. You have 3 different plots here. The x-axis is a number of training steps. Just think of it as an interaction of an agent with the simulator. The y-axis is something we call reward. So a simple way to think of that is higher the better. And you see these different plots. These are different reinforcement learning agents. And you can see that they're reasonably learning something. Like at low steps, less than 2,000, the reward is quite low. But then it gradually plateaus at a reasonable, what we call a reinforcement learning policy. It learns how to perform the task certain well. It learns how to keep the building cool, keeping all the constraints in mind. So that was great. So I can chat a bit about one concrete example, which is chiller sequencing. So if you remember, I could talk about chillers as air conditioners, right? Think of it like in this room, let's say there are 3 air conditioners. When the room is full and it's a warm day such as this, you'll want all the air conditioners to be working. But let's say when the room is empty and it's a slightly, colder December month, you might have 0 or 1 chillers working. The truth of the matter is you want to, real world conditions, as I said, it keeps fluctuating. There's also day and night patterns. So most of these building operators, they keep changing from a certain number of chillers to the other. So the transitions are continuous. The thing is, they are not very efficient. So what you see here, the unsafe operation, That is basically how, I wouldn't say unsafe in a sense, but maybe inefficient or inefficient operations, where when you are switching from different chillers, it's switched quite frequently, quite rapidly, and that's not really good. This is mostly because they are mechanical devices, they have wear and tear, and the more you keep switching them, the more these actually get degraded. But switching also has a cost. So when you switch, can you hear me? Cool. Okay. So when you switch an air conditioner on, you notice there's a slight latency for it to actually ramp up and then go at the desired cooling which you want, right? That concept just translates to what we see over here, except that it's much more expensive because chillers are huge, clunky devices. So one task, we've seen this problem in the real world. One task which we wanted to simulate in our task suite was if we could train an agent to move from the unsafe operation to the desired operation, where there are much more smoother transitions between chillers, which is also more energy efficient and increases the longevity of these large devices themselves. So if you go slightly deeper, what this translates to us telling an RLAI agent, what we're going to reward you for doing is, we want you to keep maintaining the energy savings which you do, so minimize energy used or total energy saved, maximize that. We want you to have a chiller balance. So let's say you have 3 chillers. We don't want you to just be using chiller 1, which is your favorite, right? We want to use all of them equally, so there's an equal load on all of them. So we'll reward you for maximizing an entropy term or using each chiller equally. And there's also a temperature violation term that while you're doing all of this, make sure that the people in the room, they're not getting toasted, right? It's not too hot or it's not too cold. So you keep the temperature within the desired operating or acceptable ranges of the room. So this is basically like a scalar number which we pass into a reinforcement learning agent. And we use something called hierarchical reinforcement learning, which is an exciting area. This is a slightly more advanced in a certain sense because now you actually have 2 agents. We typically call it the manager-worker architecture, where the manager is responsible of changing the chillers. Only it can have the ability to do that. And it does it at a very coarse time scale. So like maybe over every 3-4 hours, it says, oh, okay, maybe it's getting a bit warmer, let's turn another chiller on, or it's getting cold, let's turn it off. And then you have a worker over here in the bottom in red that does much finer adjustments, such as changing the temperature of each chiller. So like changing the temperature of air conditioner. And this is at every 5 to 10 minutes. So you can think of it as like more fine adjustments, what's happening. And then for like the more abrupt ones, the manager comes into play and then decides to actually take an action, right? The intuition behind using this was we have seen hierarchical reinforcement learning work well for other sort of tasks that could be decomposed into these sub-goals. And we thought that this is something which we could use in the real world, but never had the ability to. So we started the simulation here. And not many surprises with the results. We have this 3-dimensional grid over here. These are just the 3 objectives I mentioned. The average number of temperature violations, we want it to be low. The chiller off time, we also want that to be low. And then the power use, we also want to minimize that, right? So we have this 3D grid, and we want to be lower in this grid. And you see the violet color plot, the best of both worlds. That's basically the HRL, this hierarchical reinforcement learning agent I introduced over here. It performs the best. All these other plots, HBF, high heuristic-based policy, DMPO, DTPG, these are other reinforcement learning-based techniques which are considered state-of-the-art, but our manager-worker hierarchical reinforcement learning architecture managed to perform much better, which is quite incredible. And you can see this is a short summary. It uses 16% less energy than the heuristic-based policy. This is basically what's used in typical buildings such as this. It uses 10% less energy than DMPO, which is another reinforcement learning agent, and it keeps the temperature within the range. It doesn't get outside the desired cooling range. So it performs really well. So yeah, I've spoken a lot about the good stuff. Let's talk about some of the things that it would take to actually scale this, from our limited experiments to the real world and have this, hopefully, in most facilities all over the world, right? The first is a term called sim-to-real validation. This basically in plain English means that I made a simulator, but how accurate is that? So for example, if I train an agent to do well in the simulator, how well does that translate to real world performance, right? This is actually a research challenge, just seeing talks from other universities and industrial labs. I think this is something people struggle with, and it's something which will hopefully be tackled in the future, especially for problems of this scale, which you're talking about. The second is simulation speed. I skipped a section on all the optimizations we at DeepMind did to make this faster. But does anybody want to take a guess how long it takes us to simulate like a 5 minutes interval in the real world? Oh, if it was hours, we wouldn't be doing this. Obviously, it's less than that. But it took us in the order of seconds, right? And just to put that in context, in reinforcement learning, when you play with the simple Atari games or whatever else, those takes in the order of milliseconds, if not, maybe not nanoseconds, milliseconds. So we are an order of magnitude slower than what's out there. And that basically translates to our agents requiring a longer time to learn and slowing down the pace of experimentation. So being able to have a simulation that's able to run faster and not being bottlenecked by the all the computation done on the fluid dynamics, that's something that is to be investigated. And the third is fidelity. Again, I kind of skipped that in this talk, but we made a lot of approximations to make it faster, even though it's still quite slow. But those need to be further checked. We've done a bunch of preliminary results, which I'll show you in the next slide. But I think to kind of make this scalable to different diverse industrial buildings, airports, malls, large shopping centers, buildings, we need to have larger tests on like how this, how is the fidelity. So I've condensed multiple years of research into like, I think an 18-minute talk. If you are interested, yeah, feel free to take photos. These are like 3 papers. We released all of them together at NeurIPS, the RL Real World Workshop this year. They talk about different aspects. The bottom one talks about the real world results. The top one talks about the design of the simulator itself. And the third one is on this hierarchical reinforcement learning experiment. So you can have a look at all of these. So hopefully this was useful. Also want to point out a note at a DeepMind, we are growing. We're doing a lot of work in applied AI. So if you're interested, these are some of the roles we're hiring for. You can check it out in the careers page. And yeah, thank you so much. It was a pleasure presenting at the forum and really appreciate your time here.